Okay, part L of cloud computing and big data / data engineering. Jeffrey Fox presenting. We're moving on to applications 2. We finished the basic commercial applications in the last set and also saw how they were set up. And to do processing here, we'll look at clouds in science and cyber infrastructure and the NIST uses patterns. And then we make a little remark about artificial intelligence, which we already made. Well, similar things. So cyber infrastructure is an old name from NSF. And it means distributed, it means the infrastructure that supports distributed research and learning, which is the same thing roughly as e-science, e-research, or e-education. And the cyber infrastructure links data, people, and computers. Remember in the 2015 Gartner report, we were talking about digital business linking to things and people. The business will link to the things and the people. So this definition preceded things, and the computers are laptops and supercomputers and things. And it uses the standard technology, Web 2.0 and clouds, and it adds possibly using the grid, although that's now a little old-fashioned, management, security, and supercomputers. It has actually all applications doing science. It supports parallel computing, which is for low latency between nodes, and distributed systems with high millisecond latency, where the low latency is for tightly synchronized parallel simulations, and the high latency is for distributed data and loosely coupled processing. And for parallelism, we need to do data decomposition. We gave some examples of that already. And the distributed is particularly relevant for things like biology with distributed gene sequencing, or environmental science, even more dramatic distributed sensors. And cyber infrastructure can be used for almost everything, from the video conferencing to the design of a new battery, analyzing the world's telescope data, looking at personal genomes, looking at tweets, looking at the stock market, looking at the spread of disease, looking at language, ranking institutions, and so on. Cyber infrastructure is just a general term which is usually just infrastructure in the commercial world. All right, e-science, which we can generalize to E more or less anything. I used to like E more or less anything. Now I find it's not so interesting because that's gone. A few years ago, this was a really hot area, but it's now well understood and not so hot. And this e-science came from John Taylor, I don't know, 20 years ago, 18 years ago. And it's all about, again, electronically enabled science. So using cyber infrastructure to support science. And that's what these tools and technologies would be called cyber infrastructure in the US. And they need to do better, faster, different research. We will give some examples. And e-business is, of course, what Gartner called digital business, linking businesses, people, smartphones, Alexas, and so on. And they say we can think of more or less anything from digital libraries, fine arts, having fun. That's probably the most lucrative in education. And this all corresponds to a deluge of data which you have to manage and understand, process. And you need to link people, computers, data, and that data is sensors, instruments, like all the way from giant instruments like the CERN accelerator to smaller instruments like the environmental sensor on a bird or something. And we need to link them with hardware and software networks. Okay. So here is a rich slide describing the Large Hadron Collider, which is a whole bunch of magnets accelerating protons and antiprotons and that tunnel is 27 kilometers in circumference, and they have experiments where the particles in the tunnel are allowed to collide, and then the fragments from the collision, which can be 1,000 particles, are then analyzed in an apparatus. This apparatus is shown here for ATLAS, CMS, and ALICE, and LCHB are other experiments. Not, CMS will be as big, the other one's not quite as big. And it's giant. Look, here's the people working on ATLAS. And there are actually 3,000 people on a single experiment. 175 institutions, 38 countries. So this is surely what people call big science. And then we need to take the raw data, which is actually triggered. If we don't take all the data, they need to do a strong selection for data of interest. We take the raw data, which is the measurements, like here's some raw data, which is actually a Higgs boson, and it's measured in this giant apparatus with things that detect energy, things that detect photons, things that detect charged particles, and not only their direction, but also how much they bend to be able to calculate the momentum. Every event is essentially independent. They're linked together when you do an analysis and see where unusually large number of events are, and so on. And nowadays, LHC is 50 petabytes of data per year. That didn't used to be that size. And I say sometimes they just switch off the LHC, and years go by when they upgrade it. And the LHC computer grid does the initial analysis, which is the largest part of the processing. And there are 200,000 cores, at least there were a couple of years ago, in the LHC computing grid. And they have tiers, which are just ranked by where they are. Tier 0 is CERN itself, where the data is taken. Tier 1 are facilities in Europe or England or US. And Tier 2 are regional facilities. You can have any number of those. So here's some numbers. CMS, a different experiment to ATLAS with similar, has 7 Tier 1, 50 Tier 2, and it succeeds in getting all those people to work together. Here is first of a couple on astronomy. We have just here pictures. Here's the square kilometer array, and these are all in different wavelengths. Here's the classic large telescope, Mount Palomar. There's also the telescope in the sky, Hubble. And here's the Sloan telescope, which is aimed at producing more data very fast, and it's meant to cover a wide range of topics. All right, here's some multi-wavelength astronomy. And here you have the same region of the sky taken in different wavelengths. Actually, the prettiest is probably visible, where you can see this beautiful galaxy. And then if you look at it in different wavelengths, far infrared, radio, visible, X-ray, dust map, galaxy, you get these dust maps and galaxy density maps. So this would require higher resolution data. Okay, here's the next one, Polar Grid. This is a collaboration, Indiana, Elizabeth City State, and Kansas. We have data taken by aircraft, by towing them, like we see here. And that data just looks down into the Earth and looks for snow layers. It looks for glacier beds. That has to go kilometers down. That data is then sent off to Polar Grid sites in Indiana, Kansas, and Elizabeth City State. Here's the lab at Elizabeth City State. Here's a pretty frozen-looking wireless device, I think. And they build those sleds in Kansas. Everything gets shipped by our favorite shipper, FedEx or UPS. And here it is being dragged along. So this is sort of contributing to climate change studies. and by very directly finding out what mapping the gas is. Here's another well-known example from NIH, the gene sequencing cost. And here's the cost of sequencing gene. The first one cost $100 million, and nowadays they're $1,000. And this plot shows a contrast with Moore's law. Moore's law hasn't had any revolutions, but around 2007, there was a revolution, and the cost to sequence a gene dramatically decreased. Now it's more or less leveled off at about $1,000. Here is a sort of access chart, which is particularly useful for science. I call it 5A because Bob Marcus had a 5. And here we have what happens in the field. Sometimes the data comes in like this, streaming in directly from the field. Other times, like in the Croesus one, it gets stored on local disks. The disks get flown by aircraft from the North or South Pole and to Indiana University. And so we do this local accumulation until that accumulate gets big or full, and then you send it back to copy off and to resend this back to the Arctic. All right, here we have another slide on artificial intelligence and deep learning. So in business, at least, it's essential. It ought to be essential in science. When we talk about deep learning, it's part of artificial intelligence or machine learning, and you need to look at machine learning in big business packages. This if you're from business. If you're from science, you wouldn't look at these packages. You'd look at Spark probably, but that's all. And you also would, for science, you would look at the Python package and things like that. So deep learning obviously has lots of important features. It uses a few very powerful computers. It has very large data sets for training. And there are lots of efforts to make this easier used, such as from NVIDIA and others. These are just packaging this capability more easily. And then buried inside that, there's systems like TensorFlow from Google, Caffe from Berkeley, Piano, Torch, and the Microsoft Cognitive Toolkit, which was just came along. It's an impressive system, but came along a couple of years after the others. So that's the last slide of this set, and thank you very much indeed.